Okay, welcome to workshop number 4. We are going to have to do this all online until further notice. So anyway, welcome. So what we're going to be talking today about, you've been talked to you about differentiation before, but let's talk about logarithms. Logarithms. Okay, the first question is, what is a logarithm? Because logarithms actually have proved very, very, very useful to engineers and things over the years. So, I mean, what is an actual log? So let's try this. Let's try an exercise. 10 to the 0, 10 to the power of 0 is equal to 1. 10 to the power of 1 is equal to 10. Now the next question is there a number, is there a power up there that we can say is equal to, say, 3? And the answer is, hopefully. So what we do, just use our calculator, turn it on, we go log 3, and that tells us that 10 to the power of 4.7771 is equal to 3. So that number there, this number here, the power, the indice, is what we call a log. Log is basically means the indice of that power. And the most common logs that we use are going to be log 10, 10 to the power of whatever, or log e, which we'll get back to in a moment. Now, so basically this allows us to, because we can use indices now, we can use those indice rules. Remember at high school we used to say 10 to the power of A times 10 to the power of B equals 10 to the power of A plus B. And we get a log rule which is similar, which says log A times log B, log A plus log B plus log B equals log A times B. Isn't that cool? We also get another one, 10 to the A divided by 10 to the B equals 10 to the A minus B. And we can do this again. Log A minus log B equals log A divided by B. So these are related things. So basically these logs come from our indice rules. And also we get 10A to the power of B equals 10B times A, because remember we can bring that down. And we get a log rule which is pretty much the same, which goes log A to the B equals B log A. So these rules are related. So basically if you can do the indice rules, then you can do your basic log operations. So the next question is, where are logs used? And logs used. So I mean, there's a couple of places. I mean, one of the most famous one is the decibel scale. If you look at 10 decibels, 20 decibels, so decibels is rated at sound. 20 decibels is 10 times equals 10 times 10 decibels. So every time that goes up 10 decibels, then it goes up multiplied by 10. So 30 decibels equals 100 times 10 decibels. 40 decibels equals 1,000 times 10 decibels. You think about it, the human hearing range goes from 0 to about 160 decibels. So what's that? That's like 100 million times difference range that we can hear. Okay, so decibels are a logarithmic scale, and if you plot them, 10, 20, 30. It goes whoosh like that. Another logarithmic scale is the old Richter scale. I know that they don't use the Richter scale for earthquakes anymore, but 2 Richter, 2 on the Richter scale, 2 Richter, equals 30 times 1 Richter. And 3 on the Richter scale equals, well, it would be 30 times 3900 times 1 Richter. Again, we get a scale that goes like that. And these allow us to deal with very, very large numbers in a very simple, small way, which is very useful. Other places that we use logs is when we're graphing. We get 2 types of graphs. We get a semi-log graph, where this is a log scale, and this is a ordinary scale. These are great for straightening out things like parabolas. So if we were to put in a parabola, just using an ordinary scale, once we use it on a semi-log graph, we end up with a straight line. That's very useful for experimentation. You also get a log scale. And as we say in the trade, or in astrophysics, you can turn any data set into a straight line if you use a log-log scale. And the whole reason for getting stuff into a straight line is we stick in a value of x, we get out a value of y. We stick in a value of x, we get... And this makes our equations and a lot easier. So this is another place. But in reality, we notice that logs actually turn up. If you look at the amount of drug, say you go to the hospital, they give you some antibiotics, the amount of antibiotics in your system does not decrease in a linear fashion. What it does is it decreases in a fashion like that. So drug versus time, that's a logarithmic decay, what we call a logarithmic decay curve. So another one is exponential growth. So if you have, I tell 2 friends, and they tell 2 friends, and they tell 2 friends, and so number of people in the know. If I tell 2 friends, and they tell 2 friends, and they tell 2 friends, and they tell 2 friends, we now get an exponential growth rate. This is what every business actually wants. They don't get it, but that's what businesses want. They want to sell more and more and more and more and more and more. So logarithms turn up all over the place. So the next question is, we've got 2 different types, and you're going to see these in engineering a lot, especially these 2. You're going to see exponential decay, exponential growth a lot. So get used to it. So we've got 2 types of logs. We've got log 10 and log e. Now in theory, you can have any other base you want. You have log 5, log pi, log 2, log 7. Doesn't matter. Because remember, this says that number, and the log value is this number here, the exponent. So you could have 5 to the x or e to the x. Doesn't really matter. But the important thing is, these are the 2 that we're going to use the most in reality. And in fact, if you look on the average calculator, this calculator has, right here, it's got a log key, so for dealing with log 10, and it's got an ln, which means natural log, and for shifting backwards and forwards. So those are the 2 that you're going to be using most often as an engineer. So why do we use log 10? It's simple. We've got 10 fingers, and we like to count in tens. If we had 12 fingers, we'd probably use log 12. Why do we use log e? That's because a lot of stuff, particularly in calculus, revolves around e. If you use log e, it makes it a lot easier to do calculus. And in fact, you actually end up with some natural stuff, like the old joke, if you integrate, 1 over x dx, that equals natural log of x. Or if we were to do this, 1 over cabin, decabin, what we get there is a log cabin. Actually, most people think you get a nice natural log cabin, but actually you'll notice this is an indefinite integral, so it's plus c, so what we actually end up with is a houseboat. But anyway, so make sure you're confident with logs. Logs you are going to use a lot. Don't be afraid of natural logs. Remember, e is equal to 2.718 ... This is a number like pi. So what that's called irrational and transcendental. Basically this number like pi goes on forever and ever and ever and never stops and never repeats. So yeah, just be aware that you are going to be using logs a lot in pretty much every single course that you use up here. You're going to be doing exponential decays, you're going to be looking at log-log graphs and semi-log graphs, you're going to be using logarithmic scales. Okay, so anyway, I know that you got some problems to do. We've set some problems up on Moodle, so workshop 4. You will have a limited time to do them, but we're going to give you a few hours, but you can only do them on Friday. So once you get in there, go hard. Okay, and I'll catch you next week.